Thank you. And I really want to thanks again Energy Simulation for organizing this really amazing event. I really always look forward to coming and meeting all the other chairs and the research and the students at these events. Is really very basically a highlight for the year, for the research here. Today, what I'm going to present is maybe I'm trying to answer one question I was asked a few months ago. It was really, what is the value of the research that you're doing at university? And that was, when they asked me that question, I didn't really have a good answer, I think, at the beginning. And so I started thinking, really, what is the value that we are bringing by doing what I call fundamental research at the university, how we can translate that in value for the industry, and in particular, also for the energy transition effort that we are doing. Despite we are working for the oil and gas application, how we can help on the energy transition. And we saw quite a bit of talk this morning, and actually I took notes, so I'm going to refer to some of those. That is why I have my notes book here. So let's go back. What I'm looking at is really looking at unconventional reservoirs. And one thing that all unconventional reservoirs have in common, no matter where they are in the world, is that basically are all deposited in low energy marine environments. So that means that are sedimentary rock and are all finally laminated. So that is really something that is common all around the world. And that is what the rock looks like. And so you can see Montany Shale here in Alberta and British Columbia. We have Eagle Ford, Marcellus Shale in the US. We have Vaca Muerta. And just recently, I was looking at Sichuan Basin in China. Again, similar type of structure. So we should really try to see if what we were doing was really interesting in how we can incorporate and look at the effect of this rock heterogeneity in how the rock fractured during hydraulic simulation, that is stimulation, and then how we can incorporate that in a simulation. That is one thing. And Adi this morning said, well, I read, heterogeneity and fracture are very important. I totally agree. So, but that what we're looking at doing that in the lab. So I already showed these images, so I'm going through probably slides that you might have already seen. So what we did was we had the chance to actually get samples from both reservoirs and outcrop equivalent to the reservoir for the Montany, about 2.2 kilometers deep. And then what we did, we machine cubes. And then what we use is one really unique facility that was built by Professor Paul Young at the University of Toronto that is a true triaxial machine. There's many. I just visited China. If you don't have a polyaxial machine, you're nothing in the lab. Well, we have 3 as well, so we're something, but not nothing. But in particular, we have one that you can see on the right-hand side of the screen. And just for scale, you can see the machine, our sponsor at the time, and he's holding the cube. So we're using that big machine to actually apply the stress conditions that rock experiences at depth. And what we did was modify the loading platen to incorporate a mini packer that could be inserted in a mini well that we drill up to the center of the cube, and we could hydraulic fracture the samples under basically the same stress conditions that we thought the rock would experience in the lab. So, and we were really expecting to have a bi-wing crack as all the models and the textbook would have told us would happen. But in reality, it was something like much more complex. And that complexity, or actually the results were completely not what we would expect. So what we did, we tried to CT scan, X-ray CT scan the cube, but the resolution was not good enough. So we decided to actually move and actually grind the surface, so cut the surface at very small interval, 50 microns. Just to give you an idea, one human hair is about 200 microns. So we're slicing each hair in four slices and take a picture of each one of those, reconstruct everything to have a 3D reconstruction of the cube, of the fractures in the cube, actually. And those fractures would have given us the stimulated rock volume that we would have experienced. So at the end, what we did was more, we could quantitatively start to measure how those fractures will look like and were oriented with respect to the stress. And what we realized is that the fracture was definitely not bi-wing, and you can see the image there is not bi-wing. And if ever you are interested, you can come and actually hold in your hands actually a reproduction of what is this fractures network and how complicated it is becoming. But there's a few features that we can really look at. And one thing is that we can start quantifying, we can find three different families of fractures. One is a natural fracture we knew was there. Another one were parting of bedding planes that will split during hydraulic fracturing. And then the so-called hydraulic fracture, what you were expecting opening against sigma 3. Oops, what does it mean? It means that the others were not opening against sigma 3? Exactly. So the key was that most of the fracture that we measure, basically almost 90%, were not actually opening against the minimum principal stress, as we learned from the book. So the joke was, well, probably the rock didn't go to school and didn't learn about that, but it was consistently actually fracturing in a different way. And parting of bedding planes, so parting along those finely laminated planes that were common, that are common to any unconventional reservoir, was key. And almost 60%, over 60% of the stimulated rock volume was actually was parting of bedding planes. And this is something that I'm not aware of any simulators, commercial simulators accounts for. So that was a great result, and we thought it was amazing because I think we came up with a different way to see how fracture is propagating unconventional. Great. So, well, fundamentally, we need to explain why. And what we realize is that when you do test the strength of your rock, in particular, you can see in the middle a Brazilian test. So it's a way to measure the tensile strength of the material. And we tested a sample splitting along the bedding planes or breaking across the bedding planes. The strength is very different, and the difference is up to 10 MPa. And when you account that on the failure mechanism, you add that, for example, to the stress state, all of a sudden, actually, the minimum stress value that you need to overcome was exactly the one failure was happening. It was basically against sigma 2 because of the particular stress state that we were. Well, so we think that we could explain and incorporate this in the model. And well, that is, we published this research. But then what we will, oops, how do we go back? Here. No? Nope. Okay. So, but what we did during that particular study, we were asked to actually change the fluid. We use a low viscosity fluid, and we look at how the fracture was propagating, and specifically, the sponsor was interested in the breakdown pressure. And we want to compare the breakdown pressure with a high viscosity surfactant. And what he saw is that basically what we discovered is that the breakdown pressure if you use surfactant or you use just slick water, pretty much is the same. So how the fracture propagates and so on changes, but the breakdown pressure does not. And up to that time, they were convinced that they needed surfactant to actually facilitate the initiation of fracture. Well, they didn't tell us why they want to have that test. It was just a cool experiment. And of course, at university, we always look for a cool test to run because it's actually interesting. Then what we did was realize what was the impact of those two particular tests on the industry. So a few years later, so let's say 6 months ago, we start looking at how the completion changed for the operators really right after the date of those two tests. And the operators stopped using surfactant at all. That was great. So 262 wells were completed since that day with no surfactant. But they save about, I was told, about $30,000 in material per well. Not bad. Is when you go and you do the calculations, about $8 to $9 million saving. So wow, two tests, and they are saving that. It's actually a very good contribution. So I was happy. But then they were explaining me, and I'm not really a geochemist. I didn't realize that if you do inject surfactant, what it does, in a very simple words, it creates sort of a small barrier that make very difficult for the gas to flow across that barrier. So basically, your well will produce a little bit less. So I would say, okay, that's interesting. So we had the access to Enverus. It's a very nice database, so we can go and harvest all the production curve of those 262 wells and compare to the wells that were actually completed using surfactant. And we just check what was the production, how did it change? Well, I didn't realize up to this plot that every single well that was completed without surfactant is actually producing apparently about 30% more gas than those completed with surfactant. So I was amazed. So we ran just two simple tests, and that helped the industry not only to save money in material, in cost, so reduce cost, but they were making even better wells. So that was an amazing result for me to say, well, we did actually a good job, and the funding that was provided to do research was basically a good investment. And I think many of my colleagues could report really similar behaviors. So at the end, what I would like to say is that this part of the research is pointing out a few things. Is that, first of all, accounting for layer anisotropy that is present in all conventional can help in several different ways. One way is definitely can help in better model the reservoir and potentially to even generate more values because you can better quantify your reserves. But the other point is that by understanding how the fracture works, you might actually try to reduce the impact of potential value erosion. And in particular, what I'm referring to is actually induced seismic events. Because, I cite again Adi, is the curious case of fractures. those fractures might help in mixing CO2, but might also become highways for fluids to move very fast, very far away. And potentially what they could is actually migrate the fluid from the well or the area that you are trying to fracture up to maybe a critical stress fault that could trigger a large event. Well, November 17, 2015, during the operation of during hydraulic fracturing, there was a 4.28, 4.3 magnitude event in the mountain. That was definitely associated with the operation, hydraulic fracture operation, would definitely trigger. When you look at that, actually, I'm doing a little bit of advertising. I did like Rick, I didn't put the poster up, but I'm going to point to one particular poster in the room. Is actually Thomas is laughing because I'm pointing at him, and but he's going to actually explain you fully all the process that and the thinking that went behind this study. But as a matter of fact, and a spoiler for the poster, what we realized is that there were clear evidences in between a connectivity in between the injected well and the fault. So we could find all the almost the smoking gun of what happened in between the injection, so the stimulation, and the opening of a path that clearly could have connected the hydraulic operation to the fault, despite it was 3 kilometers away. And no numerical model would have predicted at the time that possibility. And it was definitely not a pressure migration, a pore fluid migration. We think there's so many evidences that will point at a direct connectivity in between the two. So basically, Thomas came up with a process for the failure that was experienced in August in 2015. And what it is basically putting together the observation in the field and the observation in the lab. So what we think it happened was that during the stimulation, the bedding plane opening played a key role. But the well was also close to one of those regional markers that are these regionally spaced weak planes that are associated with events that could be old tsunami or else, but are everywhere within the region, 400 kilometers around. And they are very weak. As a matter of fact, that we tried to sample one of those layers in Canmore where it outcrops, and when we were drilling, the fluid actually migrated to that layer and came out of the face. And it was just like another hint of how weak and how permeable that layer could have been. By doing that, by creating that connectivity, we think that the failure, the fault was lubricated, the pressure changed, and ultimately through a much more complex kinematic process that Thomas will explain much better than me in front of the poster, actually there was a major rupture that created the 4.3 magnitude event. That at the time was the largest seismic event triggered during a fluid injection in the world. Now we did much better. We went up to over magnitude 5 for geothermal. So why I'm mentioning that? Because actually geothermal and other type of stimulation are still relevant to the work that we are showing. And the other thing that is important is that you can have a large rupture, but a smaller rupture that might be associated with the casing deformation that might happen quite often during hydraulic fracturing stimulation. And to finish, I just would like to thank all the sponsors that have been supporting this work, in particular energy simulation. And I would like to mention that one thing is a Richter predictor, and I'm super happy because actually is another way that we managed to translate a part of this work into practice. So the work that we have been done has been incorporated in a product that is currently offered to support risk mitigation that could be associated with casing deformation or induced seismicity to mitigate those events. And last thing I want to say is that all this work, just taking few quotes from the talk today, I think that is an example of a way we can translate ideas and research to practice to the benefit of the industry, but it's also a way we can use innovation to have a less carbon-intensive production for oil and gas. Because if you decrease the energy you put in the ground, you increase by 30% your production, definitely is much less intensive barrel of oil or gas that you would be extracting. So it's less extensive. And last point, many of these things were Rick just explained that stiffness is important, and stiffness is actually a key part of the explanation of the phenomenon. And with that, I'm talking too long. Thank you very much for listening.
Thank you, Dr. Grasselli. Questions here? No, not yet. There's one online saying that your presentation is excellent. Have you done a reconstruction of the original block before test to see if there was any induced fracture even after test due to relaxation?
Well, we did a CT scan the block before, and what we knew, for example, for the particular one that we reconstruct, and we show that there was a natural fracture. Bedding planes were definitely closed, but we knew that were weak, and because of the mineralogy, we could see them clearly because it's an alternation on the percentage of organic matter that definitely is evident in the reconstruction, but I couldn't really see any fracture already open besides the natural fracture that was present there.
Okay. Yeah, that question was from Nader Fadin. I need to mention his name or her name. So, yeah, I think the question is obviously bedding plane. It kind of changed the whole concept of putting against the minimum principal stress. So that would require a lot of high resolution type of seismic data. What kind of resolution do you need to capture that?
Well, bedding planes are there. You know they exist because the rock has been created is a sedimentary rock, and the environment where it has been created as bedding planes. So the heterogeneity on the bedding planes, generally you can use maybe the gamma ray to have an idea what is the heterogeneities. Many companies that we are working with, they're actually recovering cores during their drilling to try to quantify what is actually the mechanical heterogeneity of these formations, in particular how weak the bedding planes are. And I think those are the two major aspects that would be nice, and that is where I was discussing with Rick, is to have a good understanding of the orientation and magnitude of the horizontal stresses that are at that particular locations, and any data that could help to constrain the stress state of the formation at depth would be amazing.
Okay.
Yeah.
Well, as I saw, you have natural fractures connecting to the bedding plane. And in a situation where you don't have natural fractures, then the classical fracture initiation and propagation may still apply. unless at some point you kind of move up or down to hit the fractures, the bedding planes?
Yes and no. In the sense, depends really what is the model that you are using for the fracture initiation. Most of the models that are generally aware of implemented, they assume an homogeneous rock.
Right.
And that do not really fully apply. If you do consider a transversely isotropic material, actually you do apply the classic fracture initiation. And work done at Monterey underground lab on opalinous clay that again is a similar material in a way, show that the fracture initiation around a circular hole that could be equivalent to the well is not really a mode 1 tension that you would expect, but is more actually a shear failure along the bedding planes than with much more complexity during the development, but basically is a slippage due to shear stress along the bedding plane. So again, you need to account for the complexity and the heterogeneity of the rock, and particularly the transversely isotropic character of your material.
Great. So as you rightly pointed out, what you're doing, beyond, it would be beyond oil and gas. It can be applied to geothermal, CCUS, hydrogen storage, anything related to injection and whatnot. So once again, thank you very much, Dr. Grasselli.
Thank you.